a certain amount of noise is inherent in any quantum system. For instance, when researchers want to read information from a quantum computer which harnesses quantum mechanical phenomena to solve certain problems too complex for classical computers, the same quantum mechanics also imparts a minimum level of unavoidable error that limits the accuracy of the measurements. Scientists can effectively get around this limitation by using parametric amplification to squeeze the noise, a quantum phenomenon that decreases the noise affecting one variable while increasing the noise that affects its conjugate partner. While the total amount of noise remains the same, it is effectively redistributed. Researchers can then make more accurate measurements by looking only at the lower noise variable. A team of researchers from MIT and elsewhere has now developed a new superconducting parametric amplifier that operates with the gain of previous narrowband squeezers while achieving quantum squeezing over much larger bandwidths. Their work is the first to demonstrate squeezing over a broad frequency bandwidth of up to 1.75 GHz while maintaining a high degree of squeezing, that is selective noise reduction. In comparison, previous microwave parametric amplifiers generally achieved bandwidths of only 100 MHz or less. This new broadband device may enable scientists to read out quantum information much more efficiently, leading to faster and more accurate quantum systems. By reducing the error in measurements, this architecture could be utilized in multi-qubit systems or other metrological applications that demand extreme precision. The research paper appears in the journal Nature Physics. Superconducting quantum circuits like quantum bits or qubits process and transfer information in quantum systems. This information is carried by microwave electromagnetic signals comprising photons. But these signals can be extremely weak, so researchers use amplifiers to boost the signal level such that clean measurements can be made. However, a quantum property known as the Heisenberg uncertainty principle requires a minimum amount of noise be added during the amplification process, leading to the standard quantum limit of background noise. However, a special device called a Josephson parametric amplifier can reduce the added noise by squeezing it below the fundamental limit by effectively redistributing it elsewhere. Quantum information is represented in the conjugate variables, for example, the amplitude and pace of electromagnetic waves. However, in many instances, researchers need only measure one of these variables, the amplitude or the phase, to determine the quantum state of the system. In these instances, they can squeeze the noise, lowering it for one variable, say amplitude, while raising it for the other, in this case phase. The total amount of noise stays the same due to Heisenberg's uncertainty principle, but its distribution can be shaped in such a way that less noisy measurements are possible on one of the variables. A conventional Josephson parametric amplifier is resonator based. It is like an echo chamber with a superconducting nonlinear element called a Josephson junction in the middle. Photons enter the echo chamber and bounce around to interact with the same Josephson junction multiple times. In this environment, the system nonlinearity realized by the Josephson junction is enhanced and leads to parametric amplification and squeezing. But since the photons traverse the same Josephson junction many times before exiting, the junction is stressed. As a result, both the bandwidth and the maximum signal the resonator-based amplifier can accommodate is limited. The MIT researchers took a different approach. Instead of embedding a single or a few Josephson junctions inside a resonator, they chained more than 3000 junctions together, creating what is known as a Josephson traveling wave parametric amplifier. Photons interact with each other as they travel from junction to junction, resulting in noise squeezing without stressing any single junction. Their traveling wave system can tolerate much higher power signals than resonator-based Josephson amplifiers without the bandwidth constraint of the resonator, leading to broadband amplification and high levels of squeezing. A pair of pump photons enters the device, serving as the energy source. Researchers can tune the frequency of photons coming from each pump to generate squeezing at the desired signal frequency. For instance, if they want to squeeze a 6 GHz signal, they would adjust the pumps to send photons at 5 and 7 GHz respectively. When the pump photons interact inside the device, they combine to produce an amplified signal with a frequency right in the middle of the two pumps. This is a special process of a more generic phenomenon called nonlinear wave mixing. This architecture enables them to reduce the noise power by a factor 10 below the fundamental quantum limit while operating with 3.5 GHz of amplification bandwidth, a frequency range that is almost 2 orders of magnitude higher than previous devices. Their device also demonstrates broadband generation of entangled photon pairs, which could enable researchers to read out quantum information more efficiently with a much higher signal-to-noise ratio. While the researchers are excited by these results, there is still room for improvement. The materials they use to fabricate the amplifier introduce some microwave loss which can reduce performance. Moving forward, they are exploring different fabrication methods that could improve the insertion loss. The researcher says that this work is not meant to be a standalone project. It has tremendous potential if we apply it to other quantum systems, to interface with a qubit system to enhance the readout, or to entangle qubits, or extend the device operating frequency range to be utilized in dark matter detection and improve its detection efficiency. This is essentially like a blueprint for future work.